my name is Denslow, and my final project's about one-way check valves. With the price of everything right now going right through the roof, everyone's got one at home, they use them all the time, and I feel bad they have to pay so much for them. But everyone uses one-way check valves. Now I know nobody really uses those, and they're only used in most niche water pipe systems, but nonetheless it's still expensive, and I aim to fix that with my project. The first step of the engineering or design process is to define the problem. My problem is they're way too expensive, and I want to see if I can create a version of them that is far cheaper than they usually are advertised for. The price that they usually go for when you order them or you go in and pick them up are about $15. My goal is to beat that, and I need to beat $30. Because I am doing just one check valve, I felt that wasn't enough to constitute writing a full paper about it, so I decided to make both versions of a one-way check valve. The first version of it is a swinging door check valve. The way those work is it has a plate that moves when water comes through, or gas or pressure, and then it closes when it's not, which blocks anything coming in the other direction. The second type is a gravity-fed ball valve, and it's not kind of like the one that you might think of when you hear a ball valve. You don't turn, it doesn't lock it. The way it works is when something moves it, a little ball or a marble gets moved up out of the way and then falls back down, and anything going down can't get past it. And lucky for me, I work at an Ace Hardware. Ace Hardware, if you've never been to one, typically has many things you can think of that you would need for plumbing, doing carpentry. So because I know the area and I know that we have a bunch of plumbing supplies, big and small, I decided that I probably could make one for even cheaper than the $15 and $25. I ended up bumping down my budgets on both types down to $10 and $20. The goal was to use PVC because PVC is cheap and it can still be used as an inline type of one-way check valve. First, we needed to figure out how we were going to set it up. Now, a lot of people around do a very similar type for a ball check valve, and the way that it works is they have a little piece similar to something like this, or they would use like a piece of rubber tube. On the inside, you can see there's a little ledge. I don't know if it's going to get it, but the little ledge, you want to find a marble or a ball bearing that can fit perfectly in there, and then seal it with a rubber gasket. What that'll do is when the ball ends up falling back down onto it, is it will keep a pressure-tight, watertight seal on it. The next thing I had to do was I had to get a bunch of actual pipe. Otherwise, the ball was just going to fly out. I had to keep it stuck in there. So what I ended up getting was this little concoction here. Now, it doesn't have the top on it, and that's just because I had to take it apart to take some pictures. But if you look in, you can see there's a marble on that side and a long tunnel before it gets to it. So this, in theory, if I blow through this end here, you could hear air. But when I flip it over, you can hear it blocks it. I tested that with water, but I felt putting water near my phone probably wasn't a great idea in showing process. The next one would be the swinging door check valve. I did a very similar step to that, where I found another type of fitting, like this guy, but instead of using a ball on the inside, I had to move a piece of plastic. So I ended up grabbing a spring, a bunch of hot glue, or super glue. I had to pay probably most of my budget on super glue just because it wouldn't fit, and I kept having to retake it out. And I had to put a little piece of nylon plating in there, and I attached it on the inside of the spring. Now, what that did is that allowed water to go through it and then have it get sprung back up into blocking the hole. In order to fix that, because it's not going to be a perfect tight seal, I had to get 2 layers of rubber O-rings and one of plastic, just so it didn't cycle back down into itself. I don't have that one with me right now. I brought both of them up with me for my Thanksgiving, and I've left half the stuff there. But it would look similar to this, but a little bit thicker and a little bit taller. That being said, moving to the second step and the third step, I kind of mixed them both in the same one. The second step, the only option is I had to create a new one. I couldn't bend any less to get something already made, and I feel like that wouldn't be a really good use of trying to take something, take a problem, and solve it just by buying something different. The third step, just like I explained, those were the steps that I used to make a design out on paper. Um, the hard part is it took a lot of attempts to get both of the designs to work, because obviously just putting a ball in something like this, it's gonna slide around. And I had attempts where I basically blow darted the marble and I hit my dad right in the side of the head, and I felt bad, but I laughed. And I had to find a solution to that. That solution was I had to sink a nail on the inside of this. It's covered up by the adapter, but it's a little 18 gauge brad nail that I just stuck through it, and I cut the side so I can slide it back. And what that did is that made the ball get stuck if it went a certain distance. Then it would fall back down. And you might be thinking to yourself, why is it even important to even think about touching one-way check valves? It's already something someone made. Why reinvent the wheel? And to that I say, backflow. Backflow is a really bad thing that happens inside systems, and if you're in any discipline of engineering, you should know about it. Backflow, essentially, in an example, is fluid traveling through some form of tube or pipe and bouncing off and coming back, and that will drag away some of the fluid, which could starve the system that requires the fluid. A good example of this is gasoline. If gasoline can't get to your engine and it comes back and it loses pressure, your engine could stall out and it could start to break stuff. Well, that's never a good thing. Um, Backflow is pretty essential in fluid mechanics, and fluid mechanics is something that almost I think every single engineering discipline uses. I'd like to go into mechanical or civil engineering, and in civil engineering, it's important to know that for, I would say, using sewers as an example, being able to move liquids certain directions, and that was kind of what got me to think about making this one-way check valve. Is that's something that a lot of people just need around every place, every project they do that has anything to do with liquid. Some way to stop it and some way to restrict it just enough where it won't kill a system. Another kind of important question to think about these one-way check valves is what can all be changed in it to make it cheaper? If it's already something made and it's already been planned out and created, what could we change to make the price go down any? Now, there's, like I said, two different types that are used most of the time. The most common is that swinging check valve, the swing plate. Now, obviously, the fact that I was able to make one with a ball means you could change the plate, the thing that blocks the fluid coming through both directions, or moves. So I knew that I could replace one piece at least with something that I could get. I think I paid $3 for a bag of 100 in order to get just one little marble. But that being said, it was harder to get that to change on the swinging plate valve because I needed it still. That was one of the only parts that actually could change, because it's the only two things on the inside, is what it hits and what stops it from going past it. With the swinging plate valve, I had to work with $20, $25, and I fixed that by getting cheap pieces of nylon and gluing them together and having to kind of jury rig it up just in order for it to work. And luckily, I was able to get it to work after about 15 different attempts of it and about 20 foot of PVC pipe later. Moving further on into the final step of the engineering design process, being testing and refining the solution until you get one that's going to work for you. In order for mine to work, I decided they had to pass 4 tests, all 4 of them, in order to be considered efficient and something I could use. The first test was the budget test. We're going to call it A and B. Check A, or check valve A, is going to be the ball valve, and check valve B is going to be the swinging door. So A, I had a budget of $10, and I was able to beat that $10, and I only paid $8.89 for every single piece that was in the final design. The second design was a little more expensive just because I had to get a couple springs, and there was a lot more moving parts inside of it. And from the $25 budget that I had, I only spent $17.37. Moving on to the second of the 4 tests was the consistency test. Now, like I said, I had to make a bunch of different versions of each of these because they constantly kept breaking, or they would let some sort of fluid like air or the water that I was dumping through it. The first design broke a lot, but in the end, after I put that nail through it, it started to work every single time. And with Project B, I was able to replace the spring, which gave it just enough where it didn't bend or not move at all when there was pressure. Both of them passed with flying colors after about 20 different attempts. The third test was ease of replication. The first one, A, was by far one of the easiest ones. You could make it in about 5 minutes if you knew what each piece was. So that one, automatically, that one's passed. B, however, sucked. I had to go through and redo it about 3 or 4 times on paper before I was even close to having a design that could work. So that one, for me, I wouldn't remake that unless I absolutely had to. So that one failed, meaning that one isn't going to be as efficient as what we're going to go for. The final test, which in my opinion is probably the most important test, is how does it look? Now, the first one, really small, really sleek, about the same size as this, really thin, I was able to get that to kind of tuck away and not look so big and, eye-catching, which is kind of what I was hoping for. So that one passed. The second one, B, similar, a lot wider. Now, the problem with it being wide is it catches your eye. I think that they both passed, but I wish that I could make the disc check valve a lot smaller and more compact. And I'm going to continue to see if I can do that. But that being said, in the final design, the only one that I was really happy with was the ball check valve, and it passed all 4 of my tests. While my choice for the project isn't that groundbreaking and not that something that the entire world probably needs, it kind of serves as a good driving point. Not everything is as perfect as we can make it. It should be something everyone wants to do, where you find something and you see, hey, can I make this better? And that was one of the big concepts of why I chose to do one-way check valves. And it's important to think about stuff like that, because everything in the world could be made more efficient. Like, I took 2 different types of check valves that have already been made, and I was able to almost half the prices that they get for ones very in the same material that you can buy online. And it didn't really take too much. I mean, it took a little bit of ingenuity, thinking about how it was going to set up, about 40 pages of my book, trying to draw out little designs. But in the end, we came up with an idea, in the beginning we had an idea, and in the end we came up with a concept of proof that it is possible to recreate a one-way check valve for cheaper than it is, solving my problem. Thank you for listening. My name is Denslow, just again. Goodbye.